Hello there, welcome to Math for Electronics. Today we're going to be talking about circular functions. But before we move into circular functions, I just want to make sure that we wrap up some loose ends with our angles and triangles. In other words, our Chapter 22 fun. There was some questions about the idea of your arcsine or arctangent, or arc cosine. And so let's just do an example just to make sure that you're comfortable with this concept, because everything in this class builds, and of course what we're going to be doing in circular functions requires that you really understand this idea of not only the trig functions, sine, cosine, and tangent, but the arc or anti-cosine, sine, and tangent. In other words, what we call the inverse trig functions. All right, so first off, what the heck is arc sine? All right, so I'm just going to go ahead and note that arc sine function, also known, or AKA, your inverse sine function. All right, same thing. So if you read about your arc sine function, it is in fact the inverse sine function. So let's look specifically at that. All right. In your textbook, you may see something like this. In other words, sine to the -1. That suggests, of course, this idea of inverse, right? Inverse sine function. And the inverse sine of, let's look at, what if we had a length b divided by c. Okay, here's our visual. Okay, pretend this is a perfect right triangle, which of course it doesn't look like, just use your imagination. All right, so c, remember that is what? Remember from last time, right? It was the side opposite your right angle. That's your hypotenuse, right? And no magic here, we're just labeling that length of the side opposite your 90-degree angle in your right triangle is the hypotenuse. We're simply labeling it now as C, okay? So this is C, our hypotenuse. All right, little review from our Chapter 22 fun, right? Angles and triangles. And then, of course, here's our length B, and this is our length A, all right? So I'm just going to put little arrows here to denote. That's what we're talking about, right? So these are simply lengths of this side. That's C, our hypotenuse, length B, and length A. And then now, let's talk about this angle. What do you mean, this angle? Take a look, right? It's the angle that happens to be right smack in between. In other words, right, it's adjacent or next to A, and of course, the hypotenuse. All right, so we can actually write a function here. In other words, the arc sine or inverse sine, right, of alpha, right, that's going to be the inverse sine. Let's go ahead and make this a little more sense here. All right. All right, so if we want to solve for this guy, right, in other words, this is our unknown, right, that's our angle, all right. If we were to go back just to the good old-fashioned SOHCAHTOA, all right, in other words, here's our, right, the sine of alpha. It's going to be opposite over adjacent. Remember, so, okay, I don't want to take anything for granted here. Again, just recall, remember, SOHCAHTOA. This was our Chapter 22 fun, right? And so that's the sine of whatever, right? So for this example, alpha is your opposite side divided by your hypotenuse, right? This is a little blast from the past, review of Chapter 22. All right, so if we were to simply write what is the sine of alpha, it would be the opposite side, which simply happens to be, for our example, B. Okay, nothing magic again about this letter. It's simply denoting the length of this side opposite of your alpha, all right, divided by A, which is, of course, adjacent to alpha. Now, this is what's key. In other words, your arc why you would ever use the arc function or your inverse sine. It's because now our goal is this guy, right? We want to figure out what the heck is alpha? What is this quantity of degrees? So what we're going to do is we're going to break into this function. What do you mean break into it? Right? End of the day, we want alpha to pop out and nothing else. Right? We want just alpha, not sine of alpha, not anything else. Okay. So in order to make that happen, we're going to have to do the inverse sine or the arc sine. Remember, equivalent. This means the same thing, also known as, right? So the arc sine or inverse sine of the sine of alpha. Right? Now watch this. Right? Our fundamental algebra, right, rules that we learned way back in chapter 4, chapter 5 says that what you do to one side of the equation, you must do to the other. All right? So that's the inverse sine of b divided by a. And again, nothing magical here. It's simply the opposite side. We're calling it b divided by the adjacent side. In other words, the side next to alpha. Should point out here that it's true that the hypotenuse is also adjacent to your alpha, but the hypotenuse is always the hypotenuse, right? Even if it's next to an angle, you don't consider that an adjacent side. So your a, this is your adjacent side, this length. All right, so opposite divided by adjacent. What you do to one side of the equation, do to the other. And this is what's really cool about your arc sine function. The arc sine cancels the sine. In other words, whoosh, and out pops just what you want. In other words, your ultimate goal, right? This is it, your ultimate goal. All right, and I would say probably in chapter 22, when you talk about your angles and triangles, this seemed to be the hardest or the trickiest part of that chapter. So that's why we're taking our time here. Just make sure you're comfortable with this idea of arc sine or inverse sine. So what you do to one side, do to the other. So then, of course, alpha is simply the inverse sine of b divided by a, right? And then the key thing here is to realize, well, what does inverse sine represent on your calculator or your best friend, right? That's what we like to call our calculator. Well, let me show you. All right, what we can do, let's see. Let me go ahead and minimize this. Let's see. Let me go out. I'm just going to pull out the calculator. Let's bring in the big calculator. See if I can try to find the one that looks a heck of a lot like the one you play with. Let's see. Okay. I doubt the good old-fashioned calculator is going to have it. Let's see. Can we go ahead and pause the video? All right. All right, so now let's go ahead and see what kind of button on your calculator would represent this crazy inverse sine or arc sine function. So if you go to your calculator, take a look, right? So here's your TI, and basically what you're going to do is find it just here. Let me pull this down. Oops. Just a bit. Right. Here we go. All right. We've got the giant view here. Just one second. All right. Well, you can see it here. In this case, you would go to the blue, right? And then do you see where it says sine? And just over the inverse sine, there it is, right? So you would click on sine, right? And then because you're in the second, right, function, you'll see there's your inverse sine function. So it's your, for this type of calculator, TI-84, your inverse sine, inverse cosine, inverse tangent is going to be your arc sine, arc cosine, arc tangent. All right? So with that said, let me clear that and let's jump into an actual problem. And what we're going to do is utilize our different arc functions, all right? Our arcsine, arctangent, and arccosine. All right, so typical problem that you would encounter, right, where you would be like, you know what, I think I got to whip out these crazy arcsine or inverse sine functions. All right, so again, nothing magical about how I'm labeling this, all right, just the idea of this letter represents your hypotenuse. Why? Because it's opposite your right angle. And then for this example, right, we've got A, this distance, and B, this distance. All right, we also have alpha and beta. All right, so we have 2 angles and 3 side lengths. And of course, this is only interesting because, of course, this is a right triangle. So that's important to understand too, is that, when would you use this? If this was just any old triangle, whereas, in other words, one of your angles is not forced to be 90 degrees, then most definitely you don't have a right triangle, and then you wouldn't be using all of these neat trig functions. So that's just something to keep in the back of your mind is, when am I going to use this? Only when I run across a right triangle. Okay, that's important. All right, so let's get back to this. So we've got given the following. We're given 2 lengths, right? We're given A, which is 757 millimeters, and we're given B, and B is 602 millimeters. And so, right, as your book is infamous about doing, is that your goals is basically everything else. In other words, whatever's not given. Okay, your book will simply say solve for whatever remaining sides or angles. So what's remaining? C, of course, and it's going to be some quantity of millimeters. So notice how I'm noting my goals, putting my required units as well to remind me. Don't forget those units. And then I also don't know my alpha, right? And then this is important. I'm going to note degrees. In other words, even though I've not been told specifically what unit this is, right? The idea is you've got to conclude that it's some particular angular unit, because that's what you've got to tell your best friend or your calculator, right? So make sure in the mode of your calculator you set it for degrees. Or if you want to play around with radians, okay, then you would note that, right? You would say, instead of degrees, you would set, right, your mode to radians, and then you would note this accordingly, all right? So if units are not given, in other words, you have no idea, what alpha and beta are, right? Make that assumption, right? And then note it, whatever that is, and then make sure your calculator is talking the correct units. That's important, okay? All right, so our unknowns are our hypotenuse, C, right? The side opposite your 90-degree angle, and then your alpha and your beta. So now we're ready to rock and roll. And of course, in this case, being that we were not given any angles, this means that we're going to want to whip out at least one, if not more, inverse trig functions, okay, or arc trig functions, however you want to think of that. All right, so your choice, whatever you want to start with, but there's some things that we also know is that if you take A, in other words, the length of this side, and square it, and you add it to B, the length of this other side, square it, you're going to end up with what? C squared. Yeah. Does anybody remember what theorem this is? Pythagorean's theorem. Again, a little review from our angles and triangles. So Pythagorean's theorem, so if you wanted to solve for C, that's one of our goals, then of course, to both sides of this equation, remember what you do to one side, you got to do to the other. Take the square root. So the square root of anything squared, out pops that thing, right? So there's our C. And on this side, of course, we're going to square A, which is given to us as 757, square that, and B, 602 squared. And when you work this out on your best friend, all right, in other words, get your calculator. Let's see if I can bring this up. All right. And let's see. It's going to be very helpful here. For some reason, my calculator is frozen in time. All right, so on your end, of course, I know your calculator's not frozen, so you should be able to do this. Basically, wait, let's see, can I click on it? Yeah, for some reason it's not able to access my bottom. Let's see. Let's see if I can change the view. There we go. All right, so now I'm not so ginormica. Okay, all right, so let's do this together. So basically, in your best friend, you're going to do the square root of. All right, so square root. So for this calculator, of course, it's a secondary function there. So blue, and then your x squared. Note your square root is just above that. All right, so square root. We want 757, and we're going to square that. All right, and we're going to add it to parentheses. All right, actually, let's see. No. Back. There we go. Let's try this one again. All right, square root. All right, having issues with, there we go. Excellent. 757 squared plus, and let's go ahead and crank this out. So 602, that's our B length squared. It's going to be 602 squared. Nope. Let's see. All right. And there we go. 602 squared. Let's get that right. O, there we go. 2 squared. And enter that. And our result is 967.18, right? Right, so that's going to be our hypotenuse. So 967, and that's millimeters. All right, so this value is very important. Why? Because we can use this side now to help us calculate alpha or beta, depending upon whatever trig function we want to use. All right, so let's see what we could bring up. All right. We just did this example, but without numbers before. So let's see if you can remember this one. So if you've got alpha here, right? If you do the sine of alpha, opposite divided by adjacent, opposite, of course, 757 divided by adjacent, all right? Again, let me just bring that back to you, right? Let's see. So, excellent. All right, and actually, right, so sine, opposite, divided by the hypotenuse. And so, just a couple things to point out. Yes, you can use this relationship, right? The sine of alpha is opposite, all right? There's your, right, opposite. Let me just draw a little arrow. Right, opposite of alpha divided by the hypotenuse, which you just calculated. And then, of course, you know how to break into this function, all right, by using your inverse sine to solve. But my recommendation is not to go this way. And the reason why is because you calculated the hypotenuse, right? And even though I'm sure, right, you are very comfortable with Pythagorean theorem, and the whole square root of the sum of the squares, what if, for whatever reason, and you know it's easy, right? Just demoing here, right? It's really easy to, oh, didn't get that parentheses right, or oh, forgot, you know, didn't enter this value right. For whatever reason, right, you incorrectly calculated the hypotenuse. So now you're walking into this goal, right, as our next goal, alpha with an incorrect hypotenuse. Okay, and so that means that even though this is correct, right, opposite divided by hypotenuse, right, that's not the route you're going to want to go, because then your alpha could be incorrect. So with that said, what if we went this route? Again, just a little blast from the past. All right, I was getting ahead of myself a little bit earlier when I was jumping on alpha equals opposite divided by, right, adjacent. That's tangent, right? That's tangent. So very important. So the idea is opposite of alpha. There's your A, right? That's your 757, right? Divided by adjacent. That, for this example, B. Again, remember, nothing magical about these letters. They're simply denoting the lengths of the sides. So in this case, B is denoting the side adjacent to alpha. All right, and that was given to us as 602. So as long as you correctly wrote down from the given to here, you have a better chance of solving alpha correctly. Of course, you could do the other way. You could do the sine using the hypotenuse you just calculated, by all means. All right, I'm just giving you some tips and tricks, things that I've observed with other students who accidentally, for whatever reason, incorrectly calculated something and then worked that into the next solution, only to come up with a second incorrect problem or result. So in this case, go with what you're given. All right, so here we've got the tan of alpha, and what we want to do is break into that function. Of course, we're going to break into it with what's called the inverse tan. And we know that what pops right smack on out is, of course, alpha, which is our goal, right? That's our second goal here. And then on this side, right, algebra fundamentals, right? Chapter 4 and chapter 5 fun, right? It's the inverse tan. In other words, what you do to one side of the equation, you got to do to the other. So the inverse tan of 757 divided by 602. Let's go ahead and see if we can make that happen on our groovy little TI. Right, so what we're going to do is the inverse tan, so note blue, and then I'm going to hit the tan function, so you'll see there's your inverse tan. And then just as we noted, right, it's the inverse tan of 757. That's our, all right, opposite side. Remember tangent, opposite divided by adjacent. 757 divided by 602. All right, so that's going to be 757 divided by 602, and let's close those parentheses and evaluate it. All right, and note the result. All right, so we have 0.89896. All right, now this is important to think about. In other words, okay, so this supposedly is degrees. Let's see. All right, so you might want to go to your mode, and you might want to see that, oh man, look at what your angular units are. It's definitely not degrees. All right, remember what's highlighted, that means what's programmed. That's why that 0.89 was kind of weird, right? So instead, let's see if we can use our little arrow down. All right, so notice now I've arrowed down to radians, it's flashing. Come on over to degrees, all right? And the idea is this is what I want. All right, so I've simply clicked on my Enter key, all right? And then now, let's quit the mode and let's reevaluate, okay? Let's reevaluate, right? The inverse tan of 757 millimeters, right, divided by 602 millimeters. When you evaluate that, yeah, baby, much better solution. In other words, 51.5 degrees is actually equivalent to 0.898 radians. It's not like your calculator did anything wrong. The language that your calculator was talking at this step was radians, all right? That was the mode it was in. And then we changed the language so that now the angular degree, right? The angular units were set to be degrees. And so now we're talking degrees. So whatever we calculated in the world of angular functions, for example, this arctan or inverse tan function, now we're cooking, right? Our final result will be presented in degrees. And that is our solution for alpha. All right, so let's go back. All right, so we get 51.5 degrees. All right, so 2 goals down, 1 to go. 2 goals down, 1 to go. All right. So for this last goal, you have options. All right, you have options, and I'll note them all because there is no option that's better than the other. It's your choice. All right. End of the day, just show me your work, right? And as long as you're on the correct path and it leads you to the same answer that I get, we're good. All right. So I'm going to show you a couple different ways. End of the day, right? It's up to you. All right. So one way is to say, you know what? If I add all the angles in a triangle, what is the total number of degrees that I'm going to get? 180, right? That's the definition. Doesn't matter what kind of triangle, all right? It could be a right triangle or not, okay? In other words, not one of the angles is forced to be 90. Then, of course, you don't have a right triangle, okay? Doesn't matter. If you've got yourself a true triangle, you add those angles up. There you get 180. So let's take a look at what would happen here, right? So you've got your alpha plus your beta plus, of course, that little square represents 90 degrees, right? And we know the total is, of course, 180. All right. All right. If you subtract 90 from both sides, now we're sitting here at alpha plus beta equals 90 degrees. We just did some good work here to solve for alpha. In other words, we know alpha is 51.5 degrees plus beta equals 90 degrees. So now we simply isolate or solve for beta. All right. And if you take 90 degrees and subtract 51.5 degrees, you'll get something around 38.5 degrees. So this is one way to solve for beta, all right? And that definitely meets the goals of this particular fun little problem, right? In other words, 1, 2, 3 goals, you're done. Show me your work and you're on your way. I'll tell you though, you can also solve beta using, guess what? Trig functions. Yeah, baby. In particular, inverse trig functions. Why? Because here you've got beta, all right? And there's your side opposite. In fact, let me just clean this little right triangle up a bit. There we go. Don't want to erase this though. Wait. All right. There we go. All right, so there's your right angle. All right, so beta, now you've got the side opposite happens to be B. The side adjacent is A. Again, strongly recommend that you use what's given. Yes, you could use trig functions that involve the hypotenuse, but since you weren't given the hypotenuse, I wouldn't do that. Of course you can. Of course you can. But my recommendation is only work with what you've been given. So here we have, right, go back to the basics, right? You've got your SOHCAHTOA, sine opposite divided by hypotenuse, cosine adjacent divided by hypotenuse, tangent opposite divided by adjacent. All right, here we have opposite divided by adjacent. In other words, tangent, right? So we could take, just bring this down here, right? So you could say the tangent of beta is equivalent to B divided by A, right? There we go. B divided by A. In other words, the tangent of beta is B, which was given to us as 602, divided by A, which was 757. Now we want to break into our tan function with the inverse tan, right? So the inverse tan of the tan of beta. Inverse tan of the tan, out pops beta. That's our goal. But of course, what you do one side of the equation, you must do to the other. So here's the inverse tan of 602 divided by 757. All right, the inverse tan of 602 divided by 757. Pop over here, and let's go ahead and do that. So blue, all right, there's your inverse tan, 602 divided by 757. All right, let's evaluate that. And there's our result, 38.49 degrees or 38.5 degrees. 38.5 degrees. Very important to note your units. That's key. Make sure you note. So, right, 2 ways, right, to get the same result. You choose. All right, end of the day, it's a way, some students use this method as a way to check their work. Okay, if you do it correctly, you definitely should end up with the same result. All right, 2 ways to get the same result. All right. Okay, so now that we've covered just a little bit about trig functions and then, of course, inverse trig functions, we're going to move on to some more fun. In other words, this idea of angles of any magnitude. Any magnitude. All right. Let me go ahead and just draw just a little kind of quick and dirty little image here. So we have counterclockwise and we have clockwise. All right, counterclockwise, clockwise. Counterclockwise, that's considered your positive angles. Anytime you go counterclockwise, right? These are your positive angles. So let's say this is our 0 mark, right? And we're moving on, right, to, let's change this up a little bit. Let's make this A. All right, so here's our point A, right? If we go from A to B, all right, what we have just done, we've sculpted out a positive angle. Positive angle, all right? This will be our little, the origin of our big circle, if you can imagine, right? So there's our 0 point. And of course, now let's dot a little better. Let's say we want to go to this point. All right, we'll call it C. In other words, we're going clockwise. That's a negative angle, right? So anytime we go clockwise, that's what we're carving out, right? Negative angles, right? So going from A to C, in other words, going clockwise, you're carving out negative angles, all right? And so just gonna draw a big old circle here so you kind of can see what's going on. All right, so let's say we've got 0, right, and we have 90 degrees, right, there's our 180, bring this down just a hair, 270. From this point, what kind of angles, right, am I carving out? In other words, I go here, 90, right, continue the fun, 180, continue the fun, 270, back to, what do we call that? 360 degrees, right? Note, I'm always going counterclockwise, right? That's why I'm getting positive 90, positive 180, positive 270, positive 360, or actually 0 degrees considered, right, your a positive. In other words, your start point there. Versus, let's go the opposite way. Right? Let's do that. In other words, we go clockwise. Right? We don't say we've gone 270, but it's actually equivalent to a negative 90. Does that make sense? So we are going clockwise. Why? Because remember, clockwise scoops out negative angles, right? And then of course, if we continue the fun, right, if we get to what used to be, or what we called a 180 point, this is also equivalent to, let me just scoot this over a bit. This is equivalent to negative 180, right? So it's a negative 180 degrees. And then if you continue the fun, right, so you went from negative 90, negative 180, what the heck is this? Yeah, baby, negative 270. But the fun never ends in this class. Continue on. Bam, where are we? Negative 360. So just little takeaways, little things that are just important to understand is that 0 degrees is equivalent to 360 degrees, which is equivalent to negative 360 degrees. It's equivalent. Likewise, 270 degrees marks the same place, remember when we went counterclockwise, that someone would end up if they went a negative 90, because negative degrees says you're going clockwise, right? Take a look. There it is. All right, so this idea of equivalent angles, you'll see this introduced in your angles and triangles chapter, right? Chapter 23. And this idea of positive versus negative angles. In other words, just remember where, right? Where you started and what direction did you take to get there. All right, and so with that said, now let's go ahead and look at what would be, I'll just go ahead and throw it out here. What is, right, equivalent angles to negative 323 degrees, right, that fall between this range, right, and here's the range in question, fall between negative 180 degrees and 180 degrees. All right, so here's our first little problem. What, right, and that is, that's not really good grammar, is it? What are equivalent angles? What are equivalent angles to negative 23 degrees that fall between negative 180 and 180? Okay, don't let this wig you out, right? You already have some great examples here of equivalent angles. And so the idea is, right, we want to end up at negative 323 degrees, but we want to get there via other methods. In other words, maybe not going, which direction do you think we would go to get to negative 323? If it's a negative angle, remember, negative angle, clockwise. So you'd start here, right? You know, that's negative 90. There's negative 180, right? Negative 270. And then the idea is, oh, right? We know that negative 323 degrees is going to fall somewhere within this range, right? Because, right, going this far, we're at negative 270. If we go all the way to this point, we've passed our negative 323. Does that make sense? All right, so, right, first off, the idea is just to wrap your mind around where is negative 323? You know, where is that located on, right, our circle here, right? Where is it? So you know that it's somewhere in this quadrant. What do you mean quadrant, right? We actually call, there's a name. We call this quadrant 1, right, which are any, right, angles in between 0 degrees and 90 degrees. Then we have our quadrant 2, right, which, let's make that a 2, actually. There we go. All right. No, really, quadrant 2. There we go. From 90 degrees to 180, right, in this range. And then here's our quadrant 3. All right, that's going to be falling anywhere between 180 and 270. And last but not least, we've got quadrant 4, right? Quadrant 4 is any angles that fall within our 0 degrees to negative 90, or from our 270 to 360, however you want to think about that, because remember, these are equivalent. All right, so we know that negative 323 degrees is somewhere in quadrant 1. We know that because we made it this far, that's negative 270, but if we hit here, we've gone too far, that's negative 360. All right, and so what I'd like to suggest to you is one way, right, to figure out, you know, how would we get to what are called equivalent angles, is to remember that equivalent angles are only a revolution away from each other, right? Only a rev away, or revolution away. Okay, what do you mean rev? Remember, 1 rev is equivalent to how many degrees? 360 degrees. Yeah, baby. So if you take negative 323 and you simply, make my 3 look more like a 3. There we go. 323, and add that to 360 degrees. In other words, what direction are you going to go? Think about that, right? Here we are. If you're going to add 360, you're going to go counterclockwise, right? All right, 360. All right. Likewise, you can take 323 and you could subtract a revolution. What do you mean subtract a revolution? Notice it's like plus, a minus. Oh, negative. Hello. That means we're going clockwise, right? Remember, negative angles clockwise. Okay, so we're going around, right? A whole revolution, but in the clockwise direction. And what you're going to end up with, so let's go ahead and do that on your calculator. All right, so that's your, let me clear this, so that's your 360, all right, minus your 323. All right, so we know 37 degrees is 1 equivalent angle. All right, so I'm going to go ahead and simply note that. All right, so there's your 37 degrees. And also, we know that if we take a negative 323 and we subtract 360 or add a negative 360, however you want to think about that, you end up with this beautiful number, right? Negative, right, 683 degrees. Let me note that. Negative 683 degrees. You know, the fun never ends. In other words, what we're doing, think about it visually, right? So negative 323 degrees plus 360 is 37, right? So let me go ahead and land just, right? So we're going past negative, right, 270, and we're coming over, kind of guesstimate, let's say this is 37 degrees, all right? So here we are. 37 degrees. So we're in quadrant 1, no surprise. Remember, quadrant 1, right, is going to be any angle in between a 0 degree and a 90 degree. Okay, it can't be 0 degrees and it can't be 90 degrees. That's important to understand. Quadrant 1 says that your, let's call it theta. In other words, make my theta look more like theta. Remember, your book simply uses Greek symbols to represent an angle, right? Angular measurement. So quadrant 1, any angle that is greater than 0 degrees, right, or less than 90 degrees. That's what's going on here, right? You're in quadrant 1 versus quadrant 2. There's your theta. It's got to be greater than 90 degrees. So it can't be 90. It can be greater, though. It could be 90.1. Now you're in quadrant 2. And then, of course, less than 180. All right, quadrant 3, there's your theta, right? Can be greater than 180, less than 270. Can't be equal to 270, just, right? Can just be a hair less, somewhere in that range between 180 and 270. And of course, last but not least, in quadrant 4, it's greater than 270, right? But less than 360. All right, so that's your quadrant 4 range. So we are in quadrant 1, right, with 37 degrees. What's important to understand is that, so here we are at 37 degrees, right? If we want to take that angle and simply go, right, remember negative, right, that's clockwise. So here we are, right, this is also negative what was given, negative 323 degrees, right? If we go 1 revolution, but in your clockwise direction, right? So here we are, and right, you're going to simply add on another 360, of course, negative, because you're going clockwise. So that's equivalent to negative 683 degrees. But of course, you know the fun never ends, right? You could continue on and say, hey, if I take 37 degrees and I add another revolution, or if I take negative 683 degrees and I subtract another revolution, all right, you're going to get other equivalent angles, 397, right, 37 degrees plus a revolution, right, or negative 1043. Again, all of these are equivalent, right? These are all equivalent angles. That's what your book tries to drive home in your angles and triangles section, right? These are equivalent angles, right? Whatever you're given here, right? No matter what, you're going to end up in the same place. Right? If someone says, oh, 397 degrees, guess what? You're going to end up here. If someone says, no, 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 I want you to go a negative 1043 degrees, guess what? You're going to end up here. 37 degrees is equivalent to negative 323 degrees, which is equivalent to negative 683, et cetera, et cetera, et cetera. What's important to understand for this particular problem, right, is it's only looking for, right, equivalent angles that fall within this range from negative 180, right, just bring that over, from negative 180 to positive 180, all right? That's the range. Okay, so what that means is you look at all the possibilities, and again, this isn't all of them. There's more. Okay, remember, you just simply add or subtract a revolution, and you can keep coming up with bigger and bigger, either more positive or more negative values. But of all of these options thus far, what meets this criteria? All right, only 37 degrees, right? So this is the solution to this particular problem. So don't be tricked when your book says, what are the equivalent angles? Right? It looks like you've got to come up with a boatload of answers. No, you can investigate. You can kind of look and see, well, what if I add another revolution? What if I subtract another revolution? You know, what am I going to get? Right? If you keep getting further and further out of your target range, then pull back and say, looks like there's only one equivalent angle to negative 323 degrees that falls within this range. And it happens to be, for this example, 37 degrees. All right, let's go ahead and try another one. All right, what if I asked for equivalent angles to 417, right? So equivalent angles, spell that right, there we go. Equivalent angles to 417 degrees. And again, we're going to focus on this range that fall within this range. Same range, in other words, negative 180 to 180 degrees. That's the range that we're going to target. All right, so what's your first step? All right, clearly 417 is what? Greater than 180. So we got to bring it back, right? Does that make sense? Right? We got to bring it back. You don't want to go, yeah, baby man, let's add 360. Whoa, right? That's going to just take you further away from this range, right? This is your target, right? This is your target. So stay here, okay? So don't add another 360. Instead, what are you going to want to do? Subtract. Yeah, baby, right? Subtract. So 417 minus 360, what do you get? I'll let you crank that out on your best friend. You'll see, oh yeah, babes, that's 57 degrees. Any more? In other words, if you take 57 and you subtract 360, it's important to understand, don't get distracted, I guess is the best word. Don't get distracted by the 180s here. I would say that's a real common problem, right? Students will see this range, and I don't know if it's test anxiety or maybe you're just not really focused on, gosh, what are we about? Oh man, we just want to figure out what angle is going to bring us back to the same exact spot that we originally were at, right? You were at 417 degrees. So you just want to come back to that same spot, but with an equivalent angle. That falls in that range. In other words, less than 180, but greater than negative 180. So you just add or subtract a revolution, right? That's all you're doing. You're adding or subtracting a revolution to get you back to that same point. What you don't want to do, and again, this is basically what most students that, again, maybe it's just test anxiety, they'll start adding or subtracting 180. Think about that. What happens? If you add or subtract 180, you're not going to get back to your home, right? Your home base is 417 degrees for this problem, right? You want to get back to 417, right? So if you add or subtract 360, you're back on track, right? You're back where you started. If you only add or subtract 180, think about that in the visual, right? Just draw yourself a circle and say, oh, man, I'm the exact opposite from where I'm supposed to be, right? Where 417 is, I'm like 180 degrees away, because that's all you did. You just added half of a revolution, right? Remember, half of a revolution, half of 360, 180. Okay, so don't let that target, the range of negative 180 to 180 trick you. That, I would say that's probably the trickiest part about this chapter, really, is that students just get distracted by the goal. The goal is to get yourself back home, right? Equivalent angle. Add or subtract 360, you're back home, all right? And then it's just a matter of, can we get in that target range? So if we're here at 57 degrees, right? So we know, right, that 57 degrees, right, is one equivalent angle. So it doesn't hurt, right? Even if your book doesn't tell you to do this, go ahead and draw yourself, right? Remember your different quadrants, 1, 2, right, 3, and 4, right? And just quick and dirty, that's 0 degrees, that's 90, that's 180, right? This is 270, right? So by subtracting a revolution, right, basically 417 degrees is the same place as 57. In other words, you're somewhere, really guesstimating here, but somewhere about there, right? In other words, this is your 57 degree mark, right? We've gone 57. So you're in quadrant 1, right? Right? This mark, 57 degrees, is in fact 417 degrees. Think about it, right? 90, 180, 270. Remember what this is. 360 is an equivalent angle to 0 degrees, right? So you know, if you go all the way to 90, you've passed 417. So this is 417, right? 417 degrees is 57 degrees. It's the same point on your little circle here, right? So either you go 57 or there's your 360 plus there's your 57, right? Brings you to 417. They're equivalent. And if you continue the fun and say, well, you know, 57 minus 360, gosh, is that going to be in my range? So come on over here, say 57 minus 360, right? What you're going to observe is that, ooh, negative 303, that's out of that required range, right, of negative 180 to 180. So you don't want to go there. And if you're still thinking, well, you know, so negative 303, that's not in the range. But what if I did 57 degrees? Actually, let's do this. What if I took my 417 and instead of subtracting 360, I added 360? Well, gosh, even without a calculator, you see that, oh man, if I'm adding 417 to 360, right, I am like way past 180, right? Way past, right? So, right? It looks like no matter how many other times I add or subtract a revolution, I am getting farther and farther from my targeted range, right? You want this range. You want to be less than 180, greater than negative 180, which happens to be this one equivalent angle, 57. Yes, 57 degrees is equivalent to negative 303 degrees, which is equivalent to 777 degrees, right? In other words, no matter what, you end up at the same place, right? If someone says, go negative 303 degrees, bam, there you are. If someone says, no, I want you to go 777 degrees, bam, there you are, same place. You end up here, right? Which is equivalent to, of course, our targeted, right? This is the one equivalent angle that falls within our targeted range. That's what you're talking about. All right, so typical problem, right, that you'll be doing a lot of actually in your angles and triangles section. A lot. All right, so the next thing, and actually we've already touched on it, so let me just continue the fun, right? We've talked about our quadrants. Okay, so the next fun thing that you're going to be doing in your chapter 23, right, your circular functions, is actually you're going to be given angles that you then have to locate, right, on what's called the complex plane, right? In other words, where you see your quadrant 1, 2, 3, and 4. So let's look at that, all right? So we've got, for example, let's say you are given 135 degrees, and you are simply asked, right, which quadrant does 135 degrees fall into? So here's our, right, complex plane, okay, and of course, 135, you know you go 0 to 90, and now you're out of quadrant 1, 90 to 180, hello. Right, so you see that actually your 135 is going to fall somewhere here. All right, it's not going to go into quadrant 3 because quadrant 3 is from 180 to 270. All right, so your answer, right, is quadrant 2. All right, so that's simple. Okay, not really much work to show me here. Okay, just make sure you get it right. All right, what if you were given negative 100 degrees? Right, and again, same goal. What quadrant does negative 100 degrees fall into? So here's your complex plane, Remember, if it's negative, what direction are you going to go? Could be, yes, clockwise. All right, so here we go, 0 to 2, 7, actually. 0 to, what is the negative equivalent? What could it be? Negative 90, perhaps, right? Remember how this works, 0 to negative 90, right? This would be negative 180, right? Continue. Of course, 90 degrees is equivalent to negative 270. Remember, these are all equivalent, which comes right back to, of course, 0 degrees is equal to 360 degrees, which is equal to a negative 360 degrees. It's all, right? They're all equivalent angles. So if we have a negative 100 degrees, right, obviously we're not going to be in quadrant 2. Why? Because quadrant 2 is only from 0 to negative 90. So we're moving in here, right? We're going to be somewhere in quadrant 3, right, between negative 90 and negative 180, right? So that's going to be your quadrant 3. Right? What about negative 256? Negative 256. All right. Now, of course, right, you can go to the complex plane and say, you know what, there's my, right, negative angles, right? So here I'm going clockwise. So there's my negative 90, negative 180, negative 270. Let me make my 270 look more 270 like. There we go. That's 270. Yeah, it's degrees. All right, so negative 270 and, of course, negative 360. So we know that where is our negative 256? It's in this range, right? Somewhere in quadrant 2. All right. So one way to do this is, of course, by just looking at your complex plane, and there's your negative 90, negative 180. Oh, too far, negative 270, so we're somewhere here. All right, so of course this is going to be your quadrant 2. All right, but let me show you that you also can think of this in terms of equivalent angles. Right? In other words, you know that for an equivalent angle, equivalent to negative 256, if you simply add 360, in other words, add a revolution, right, you're ending up with 104 degrees, which maybe is a little easier for you to recognize. In other words, oh yeah, 104 degrees, so it's going to be past quadrant 1, right? There's your 104, somewhere between 90 and 180. So however you get there, right? Because an equivalent angle, there's your 104, that is going to be in the same quadrant as, of course, negative 256. They're equivalent, right? Does that make sense? So, if you want to apply what you learned with your equivalent angles, and it's just a revolution away, by all means, right? Add or subtract 360 and nail it, to, look at your complex plane, say, hey, it's quadrant 1, 2, 3, 4. Or, just the idea of recall your positive and negative angles. And if it's negative, right, you go clockwise. Negative 90, negative 180, negative 270, back to negative 360, right? So lots of ways to do it. Typical stuff that you're going to be doing in your circular functions chapter, right? You're going to be working with all these cool angles and just simply trying to determine, hey, where do they live? All right, and then what you're going to see is that at the end of this chapter, you get to play with the polar coordinate system. Polar coordinate system. All right, which shouldn't surprise anybody, right? You're going to be playing around with circles, right? And of course, your book does such a much nicer job. But anyways, you get the idea. So just pretend these are perfect circles. And of course, we know this is 0 degrees, 90 degrees, 180 degrees, and 270. Remember, that's counterclockwise, get you those positive angles. All right, and what we're going to do is let's go ahead and let basically the radius of this inner circle to be 1, and the radius of this second circle to be 2, and our third or most outermost circle 3. All right, so that'll be the radius. 1, 2, 3. All right, and now take a look. All right, we've got some fun stuff here. Let's say we've got a little dot out here. Okay, we've got a little dot. All right, this little dot definitely has a home. Okay, in other words, it's reciting here, and it has, in fact, 2 types of addresses. Okay, so one type of address is this idea of describing what is the distance from the origin or the very center out to that dot. All right, that distance we call rho. Okay, and notice what it is. It's just a distance, right? It's a length from the very center to that dot, okay, this location. All right, and then there's some angle. Okay, let me see. Got Ginormica eraser here. See if I can do a better job. All right, so there's theta. Okay, so theta is this amount of degrees or radians, right, depending upon the language of your calculator, right? Actually, in this case, let's nail it as degrees since we've already set up our quadrant system and such, right? So there's a certain quantity of degrees, all right, from this 0 line out to rho, right, or the distance going out to this particular little dot, okay? You would describe this address. The address to this dot is rho angle theta. In other words, the length from the center to that dot, and then that's considered the magnitude. I'll just go ahead and just note that. Magnitude. And of course, this theta, this is your direction. This is your direction. So it's the direction that this particular line is aiming towards, and then you just simply go the magnitude of that line and bam, there you are at your dot. All right, so this rho angle theta is considered one set of directions that tells you how to get there. What do you mean there? Gets you to that dot, right? Okay, so in this next section, basically what you're going to be doing is trying to figure out, well, what is the distance out to wherever your dot is, and what is your angle, okay? Rho angle theta. All right, so what you're going to see in your book is, right, you'll see dots all over the place. For example, let's go ahead and I'll work over here, right? So let's say that we know that if you go out this distance, right, we end up, let's say we end up at 100 degrees, okay? And I'll just do another little example. We come out here, let's say that works out to be, all right, again, your book has a much nicer polar graph paper, and everything's, you know, much more specific, but you're getting the idea. So if we go out this distance, let's say we get maybe 160, maybe 160. All right. And if we come out right here, let's say this is 240. All right. And if we come out here, let's just guesstimate that this is about maybe a little higher. Let's see, maybe 340. All right, so total guesstimation. Yeah, so just pretend that this looks definitely a little more spaced out. But anyways, you get the idea. And so now what I'm going to do is just place a few dots in different locations. Right? Here and there and everywhere. Okay. And actually, let me go ahead and give this an angle too. Let's say this is about 50 degrees. Okay. All right. So if this, say, was A, B, C, D, and E, all right, the next thing is go ahead and describe what is the magnitude and direction of these various points on our polar coordinate system. All right, let's do the first one. We'll just do alphabetical order. So A, all right, so what you're going to say is, okay, that's, looks like we're going out 1, 2, so our magnitude is 2, and the angle is 50 degrees, right? So in other words, your theta, right, happens to be 50, right? So that's the angle, and we're going out 1, 2. Okay, let's work on B. All right, so B, the magnitude of B, 1, 2, 3, and its angle is 100 degrees. All right, C, the magnitude and direction of this guy is going to be, right, the distance out, that's the magnitude, 1, and its angle, right, we're going 160 degrees. Make sense? All right, let's do D. So D is in what quadrant? Remember what these quadrants are? Remember from 0 to 90? This is, of course, quadrant 1. From 90 to 180, quadrant 2. From 180 to 270, quadrant 3. All right, so that's, let me put the unit, sorry about that, 240 degrees, right? That's your quadrant 3. And then last but not least, there's your quadrant 4. All right, from 270 to 0 degrees, which is also equivalent to 360. All right, so if we're focusing on D, the address of D, right, and the world of polar coordinates, that's what we're coming up with, right? These are polar coordinates, right? It's going to be the magnitude, right? So the magnitude out, 1, 2. And then, of course, the direction, 240, which is equivalent to what? In other words, you could do 240 or what else? To what? What would be an equivalent angle to 240? Have we talked about equivalent angles today? Right? Yes, we have. Well, I guess depending on whenever you're watching this video. It could be tonight. All right, 270 minus 360. Remember, it's always a revolution away. Right? So if we come on over, right? Actually, yeah, 240. There we go. Let me clear this. Right, so 240 minus 360, negative 120 degrees. That's equivalent, right? Remember, equivalent angles are a revolution away, right? A revolution either plus 360 or minus 360. So 240 degrees is negative 120, right? It's all the same, right? So minus 120 degrees, right? So we can actually write that, right? We could totally put, you know, negative 120. It's the same thing, right? Now the magnitude, though, is positive, okay? It's the length, okay? That's all that is, right? But the direction could be positive, positive 240, or it could be negative, negative 120. It doesn't matter if you give your answer in positive or negative. You're just simply saying either you go counterclockwise, right? So there's your positive 240, or if you note down a negative 120, then you're simply telling someone to go clockwise, right? That's the difference between positive angles and negative angles, is the direction. That's it. Are you going negative? Oh yeah, baby. Or are you going positive? If you're going negative, of course, that's clockwise, and you end up at the same point. You end up here, right? You end up at D. Okay, so on an exam, I take either way, right? You could most certainly convert it to a negative angle, as long as it's equivalent, as long as it's a revolution away. That's key, all right? This is your revolution. You add or subtract 360, you're scot-free. All right, last one to look at. How would you address E? You have choices, all right? You know the magnitude. You don't have a choice there. Pretty much it's magnitude of 3, right? So in other words, that's your distance out. And then your direction, your choice. If you go this way, right, so there's your theta going this way, that's going to be what? Right, if this is 340, right, so you'd say 340 degrees minus a revolution, right? So here you are, 340 minus 360, and there it is, right? It's a negative 20. So your choice, you can put negative 20 degrees down, or you could say a magnitude of 3 angle. No, we're going to go this way, right? We're going to go bam, right? So we're going to carve out a positive 340 degrees. Right? However you get there. You will end up at the same location. Negative 20 degrees is equivalent to positive 340 degrees. Same thing. All right? So that's how you're going to actually end all of this circular function fun, right? This is chapter 23 if you haven't figured that out yet. And don't skip a single problem, right? I call your textbook exercises your exam prep problems for a reason. They do prepare you for any exam in this class, so don't blow them off, right? Really make sure you're completing them and having fun with them. Ask questions, have study groups, ask questions of your colleagues, ask questions of me, right? That helps to, make sure that you're going to succeed not only on our next exam, but of course, in the course, right? And then future, right? Future courses, because what you learn in this course just builds, right? What you learn, you're going to take with you to the next level. So don't blow it off, right? Really try to take that time, work through the problems, really, put yourself in whatever situation that you best learn in, right? If you're a person that needs people around you, then get study groups together to kind of, keep you accountable. So you're really making sure you're completing those exam prep problems and you're getting your questions addressed. If you're the kind of person that needs silence and you just need to be by yourself and find that place, right, where you have quiet and you don't have a lot of people around you. And then if you hit a brick wall for whatever reason, right, you can contact me. Remember, we're also all connected in Blackboard, so you can email the whole class, right? So even if you don't have a study group, right, basically you do. You have a virtual study group with the entire class. So at any time, shoot them an email and say, hey, I'm stuck on chapter 23, this particular problem, what's going on, right? We're all in the same boat, and it's not the Titanic, right? You know that. So stay strong, keep up with the assignment, ask questions, and you will do well in this class, I promise. All right, and with that, I'll see you next time. Take care.